When we talk about NMR spectroscopy and how it relates to all of the other forms of spectroscopy, there's a number of different ways we can do that. One of them is simply the transition that the light causes on our atoms or molecules. Gamma rays, for example, the highest energy form of spectroscopy that we typically will run across from time to time, basically takes the electrons and strips them completely off an atom or molecule. It's such an energetic technique. Whereas NMR spectroscopy, the lowest energy technique that we run across, basically just simply reorients the orientation of a magnetic nucleus in an external magnetic field. There are other ways of talking about spectroscopy involving the numbers, typically wavelengths, frequencies, or energies. Here are these various numbers all in common units. I'm using energy in kilojoules per mole. Those are the types of energy units that many chemists are most familiar with. And you can see here again comparing gamma to NMR as the two extremes on here, that gamma rays or gamma spectroscopy uses by far the shortest wavelength, highest energy, highest frequency light, and NMR over there is the lowest energy, longest wavelength, and lowest frequency light typically used in spectroscopy. There's another way of talking about it are the typical units, the units that spectroscopists who work carefully in each of these areas might use. For example, the X-ray and gamma ray spectroscopists often will talk about their spectra in terms of energy, either kilo or even mega electron volts. The UV vis spectroscopists and the IR spectroscopists will often use wavelength. We talk about the wave in UV vis, the wavelength of light that causes a transition in nanometers. The infrared spectroscopists studying molecular vibrations will also use wavelength, often a modified wavelength we call wave numbers or reciprocal centimeters. The microwave and the NMR spectroscopists will typically use frequency units. For example, our particular instrument is a 400 megahertz NMR spectrometer. Oftentimes there are modifications made to these units. For example, in NMR spectroscopy we will often, instead of using 400 megahertz and variations of that, we will use something called parts per million or ppm. The critical thing about comparing all of these is to realize that things like gamma spectroscopy and X-ray spectroscopy, these are sledgehammer techniques. These techniques have the highest energy and really make modifications for the molecules and the atoms that are being studied. NMR is a much lower energy technique. It's almost like tapping on your molecule with one of the most delicate little tiny hammers you can imagine. Being a low energy technique gives NMR some advantages and disadvantages. The advantage is it is likely the most information rich form of spectroscopy that we typically will do. The disadvantage, of course, is going to be that it's probably the least sensitive form of spectroscopy, in that we need relatively high sample sizes compared to some of the other types of spectroscopy to get the information that we are so interested in obtaining. The last bit to think about in comparing the various kinds of spectroscopy is simply learning how to convert between wavelengths, frequencies, and energies in all of these types of spectroscopy, just to get a feel or an understanding of the calculations involved in that. And that's the part we'll look at next.
Valuable skill when you're looking at NMR or any form of spectroscopy is to be able to convert between the various units each type of spectroscopy uses. Some, of course, favor frequencies, some wavelengths, others modified versions of those, and still others the energy values of the light that's being studied. And so I wanted to run through a couple of sample calculations on how we convert one into the other, because it's helpful sometimes to put NMR in context with the other types of spectroscopy that you may be familiar with from previous classwork. This is the basic toolkit you need to be able to use in order to do that. The energy of light equation equals h nu, okay, Planck's constant and frequency. The speed of light equation, wavelength times frequency, and that one is a constant, 3 times 10 to the 8th meters per second. And then the constants themselves, good old Planck's constant, 6.626 times 10 to the negative 34 joules seconds. Kind of fun to say that one, the speed of light. And we are actually going to use our dearest friend in chemistry, Avogadro's number, 6.02 times 10 to the 23rd number of anything per mole. So as an example of doing this type of thing, I have my, classical red laser pointer here, which, generates one of those bright spots here that you see in various classes sometimes. And it's printed right on the laser pointer that this thing generates a wavelength of light at 640 nanometer wavelength. Okay, right there in the red region, you see kind of the bright red photons. And what we're going to do is convert that into frequency and energy, and actually a different way of expressing wavelength called wave numbers that's common in IR spectroscopy. So briefly, here's what the type of question would look like. So the first thing we're going to do is turn that wavelength into frequency. And to do that, of course, we need our friend, the speed of light equation. Okay. And now we're asked for frequency. Question mark, what is the frequency of light at 640 nanometer wavelength? No great surprise. We need to solve it for wavelength. Solve it for frequency, excuse me. And that's a pretty standard sort of thing to do. There is going to be one issue, though. If you just blindly start plugging in numbers, okay, 3.0 times 10 to the 8th meters per second as the speed of light, which is a constant, divided by the wavelength, they'll give us 640 nanometers. If you're not careful, you should look at that right now and go, uh-oh, because there is an issue here. And yes, our units aren't matching, okay? We have meters on the top, nanometers on the bottom. If you blindly started plugging away now, you will get go off the rails here. And so yes, this is a fairly common thing that will happen when you're doing calculations here. You'll often have to convert, nanometers to meters and other sorts of things like that. Pretty basic stuff, but, good idea to remember how to do it. I'm going to turn to 640 nanometers into meters. It does require us to remember what the definition of nanometer is and some of the other metric prefixes. Remember, nano is billionth, so a nanometer is a billionth of a meter. And so it takes either a billion nanometers to equal 1 meter, and that's how you express it here. 10 to the 9th is billion. A billion nanometers is 1 meter. You could also say that that a billionth of a meter is 1 nanometer. That would work perfectly well, as perfectly fine as well. Doing this sort of calculation, you come out with 6.4 times 10 to the negative 7th meters. And so now if I use that as my calculation, the speed of light divided by 6.4 times 10 to the negative 7th meters. Now my units cancel off beautifully. And you will notice that I'm left with seconds as the only unit left, but it's meters per second. It's in the denominator. And so when I do the calculation, and I often do these and slip them over here on the side so I don't have to sit there and calculate it. What I came out with was 4.7 times 10 to the negative 14. And it's reciprocal seconds, okay? It's seconds in the denominator, often called 4.7 times 10 to the, that should be positive 14, excuse me. 4.7 times 10 to the 14th, a big number, times 10 to the 14th, reciprocal seconds. You will also see that written sometimes as hertz, okay, technically cycles per second. And so there is the standard frequency unit, okay? Photons of the red light are oscillating 4.7 times 10 to the 14th times each second, okay, which is quite a bit. Okay? So there it is. There's the wavelength expressed as frequency. What I'm going to do is apply the magic eraser, save that number, and we'll move on to the next one. The next one was energy. Okay, what is the energy of light at 640 nanometer wavelength? And of course, we're going to use the little energy of light equation. Now, we're going to express this not in standard chemistry type units of kilojoules per mole. Okay, there's of course a million ways to express energy. There's a myriad of units you can use. We're chemists, and so kilojoules per mole is kind of an energy unit we feel comfortable with. So that's what I'm going to do, is get the energy of 640 nanometer light in units of kilojoules per mole. To do that, of course, we're going to start with this. So we need Planck's constant, 6.626 times 10 to the negative 34th joules times seconds, times the frequency, which we already calculated, 4.7 times 10 to the 14th reciprocal seconds. When you punch that out in your calculator, yeah, your scientific notation button is just going to have a heyday with this stuff. But notice the units. We have joules times seconds and reciprocal seconds. Yep, the seconds are going to cancel, which is kind of convenient, leaving us with joules as our energy unit. And when you punch that out, 3.1 times 10 to the negative 19th joules. Now, that seems like a really small number. It is a really small number. But I want you to recognize one thing. This is the number of joules in one photon of the red light. Okay? That is the amount of energy in one photon. One photon doesn't pack a whole lot of energy, but of course, we rarely are dealing with one photon at a time. We're dealing with large numbers of them, and that's why we're going to go for kilojoules per mole. Getting this into kilojoules per mole is not that difficult. Of course, we're simply going to multiply it by every chemist's dearest friend, Avogadro's number, 6.02 times 10 to the 23rd, which is the number of anything, including joules, in 1 mole. And if we punch that out in your calculator, more fun scientific notation, 186,977 joules per mole. Okay? Which, okay, now there's a big number. Oh, it's joules per mole. That's not actually all that large. Our standard is kilojoules per mole, and so rounding off just a bit, 187 kilojoules per mole. Okay, so there is the energy of light from the red light laser expressed in standard chemistry type energy units. Okay, so there's that one, and on to the last one. For the last one, we're going to actually go for a little bit of an odd unit, wave numbers. This is more typically seen in IR spectroscopy. If you remember, IR spectra are expressed in wave numbers. They're defined as reciprocal centimeters. Okay, it is just the unit that group of spectroscopists uses to express the energy, the values that they're measuring here. It's not a typical visible light unit, but I just wanted to do this particular example because yes, any of these types of units can be converted into any of the others. Okay, so this is kind of a funky way of expressing wavelengths, not as the actual wavelengths, but as reciprocal wavelengths. So we're going to take the 640 nanometers, and it's a pretty simple process to do. It should come as no big surprise. I'm going to turn that into centimeters, okay? And if you express 640 nanometers as centimeters, you get 6.4 times 10 to the negative 5th. You get 6.4 times 10 to the negative 5th centimeters, okay? And reciprocal centimeters, ooh, no surprise there, is the reciprocal of 6.4 times 10 to the negative 5th centimeters. And when you punch that on your calculator, I get 15,625 reciprocal centimeters. And that's kind of an interesting number when it comes out. If you remember, in IR spectroscopy, when you look at an IR spectrum, the standard numbers are generally from about 4,000 wave numbers over to approximately 600 wave numbers. This is well outside that range, but no surprise, it's visible light rather than infrared. But I just did it to show that these are all essentially the same number, just different ways of expressing light, looking at its wavelength, its frequency, its energy, and sometimes modified versions of those, like this modified wavelength here we call wave numbers. It's a common sort of thing to have to do from time to time, so there are the basics of how to do these calculations. Practice it a few times, and we'll talk to you later.